So in the last video, we took a look at how we could determine the exact area under a curve by setting up in kind of a Riemann sum with n rectangles being used, and then applying a limit as the number of rectangles approached infinity. So while this represents the exact area, like the area up here in red, as I state below, the next logical question would be, well, how the heck do you evaluate a limit like that, right? Like, this is ridiculous. Like, yay, the area is equal to this mess, but I don't know what to do with this mess, so how is this even useful? Well, it's actually really surprising to find out that at times it's really easy to calculate limits like this, as long as I'm aware of the following facts. Now, if I take a look at these facts, I can try to understand what exactly it is that they're saying. Notice here that this first fact is telling me what it would look like if I was going to add something that is I when I starts from 1 and goes to n. This first addition problem here says if you're ever adding 1 plus 2 plus 3 plus 4 plus 5, if you're ever adding just one number after another up to a value of n, here's what it's equivalent to. Similarly, if I was adding squares of numbers, 1 squared plus 2 squared plus 3 squared plus 4 squared, all the way up to n, that is all the way up to n squared, here's a formula that tells me what that actually turns into. And you could actually test these formulas. Notice down here it's the same thing, but for a value of stuff that's cubed. Now, these are facts that can be proven using the idea of mathematical induction. If you're not aware of what mathematical induction is, you've never heard of it before, it's an awesome idea and one that if you're planning on doing a lot of work in later, like a lot of math classes into the future, might be helpful to at least have heard of before. So I'm more than happy to talk with any of you about that topic if you're interested, but it's a common proof technique that's often discussed in a pre-calculus class. So we're going to go ahead and be aware of these ideas and see how we can maybe use them as we actually try to find this exact limit that we set up here in example 2, down here in example 3. So I want to determine the exact area, again, that exists between the curve of f of x equals x squared. I'm going to draw it out again over here on the interval from 0 over to 2. So again, I'm looking to find this exact red area in here. I want to know precisely how much area there is. Now, according to what we had in example 2, we know that that amount of red area is equal to a limit as n approaches infinity of a giant summation where I starts at 1 and goes to n. And then we had a 2 over n times an I, all squared, times a 2 over n. Right? So this is what we had set up from example 2. But how do we compute this? Well, let's take a look. I'm going to go ahead and make use of some of these facts up here to show how I might be able to do this a bit more easily. First off, my goal is going to be to simplify the inside as much as possible until it resembles something with no summation symbol whatsoever. So let's see how I'm going to do that here. Well, some of the first things that I might note that I could do with this summation that I have here on the inside is I could start to simplify, say, this quantity that's squared. Notice if I was to square this quantity, I would get 4 over n squared times an I squared. And then I would have times a 2 over n. Now, of course, I could now multiply some of my fractions here together, and I could rewrite this one more time. This would still be then a summation as I goes from 1 to n, but now I could say I have 8 over n cubed and times an I squared. Now, when I take a look at this, this is going to be kind of a very, very interesting sort of a summation. And I can think about kind of what it's going to look like. Notice that what this summation is calculating is something like the following. If I is the value of 1, then notice I'm going to get 8 over n to the third times 1 cubed. If I is going to be improved then to the value of 2, I'm going to get 8 over n to the third and then 2 cubed. Or sorry, not cubed, these are squared, excuse me. If I now goes up to the value of 3, I'm going to get 8 over n cubed and then 3 squared. And this is just going to keep going. So what do you notice is going to be in common with every single thing produced by this summation? Is there something in common between all these terms? Yeah, the 8 over n cubed is always in common, right? And so what I can do here is I'm actually going to go ahead and I'm going to imagine factoring out this 8 over n cubed. Notice that would leave me with like 1 squared plus 2 squared plus 3 squared and on and on and on. But all of that would be pulled out of this. So to see what this would look like, I can go ahead and express it maybe in the following way. I would have 8 over n cubed pulled outside of the addition problem. And I know I can pull it outside because it's common between all of the terms. It's not changed when I changes. And so what I would have left then on the inside is just this I squared. So you can see I've kind of just taken this 8 over n cubed and I've pulled it outside of the sum, kind of like I've undistributed it. I've factored it out. Well, now I can make use of a really cool idea from up above. Notice that up here I'm told that if I ever see a summation of just I squared, it is equivalent, that whole set of symbols is equivalent to these symbols here. N times n plus 1 times 2n plus 1 over 6. So I'm going to recognize that since I have that right here, I can make that replacement. So this is going to be the limit as n approaches infinity of 8 over n cubed, and then in place of all of this stuff, I'm going to go ahead and put down n times n plus 1 times 2n plus 1 over 6. So again, I'm just making use of that blue fact that I outlined above. This stuff in blue is equivalent to that stuff in blue, so I'm just making a fair trade. Now, if I wanted to, I could go ahead and multiply these fractions together and do a whole bunch of different work with them. I'm going to go ahead here and note that if I did multiply these together, I would be moved to a limit as n approaches infinity of 8n times n plus 1 times 2n plus 1 in the top, and in the denominator, I would have 6n to the third. So notice, this actually looks like a limit that we would have had maybe, say, right near the beginning of the semester. We should be able to evaluate this limit using our knowledge from our first chapter. So let's go ahead here and simplify this down a little bit further. I'm going to go ahead and actually multiply out some of the stuff that I see in the numerator. If I distribute my 8n into my first set of parentheses, I'm going to get 8n squared plus 8n. I would still have to multiply that by 2n plus 1 to fully multiply out the numerator. Now I'm actually going to go ahead and do that here. I'll skip a little bit of the detail and just tell you what I get for the final solution. You should be able to confirm, though, that what I'm writing here is indeed actually correct. I believe I would end up with a 16n to the third plus a 24n squared plus an 8n after I multiply all of the numerator out and combine all the like terms. In the denominator, I still have a 6n to the third. And again, I'm still interested in evaluating this limit. So how would I do this? Well, you might be able to see that, well, what if I came in here and I multiplied top and bottom here by 1 over n to the third power? You might recall this was something that we could easily do. I'm just multiplying by a value of 1. I'm picking this because I have a limit as n approaches infinity, and n to the third is the largest power of n I see in the denominator. So notice I would get 16 plus 24 over n plus 8 over n squared in the numerator, and in the denominator I would just get 6. Okay, so if this is what I get down here, and now I have the limit as n goes to infinity, notice I can calculate that limit really quickly. That's going to be 16 plus 0 over 6, and I am going to come up with a final value for this at 16 over 6, which I could reduce to the value of 8/3. So we just computed something. What did we just compute? We finally computed this giant limit, and that limit represented the area of this region. This right here is the exact area up above. This area is a total of 8/3. We were able to evaluate one of these difficult limits. We did it. We found the exact area. So the goal of this section is going to be to continue to try to find exact areas by using this concept of Riemann sums and their limits as n, the number of rectangles, approaches infinity. This is going to require that we get some practice with using these facts that were in the box here, as well as understanding some different forms of notation and other things that we can do to communicate these ideas a bit more simply and directly.